Now that we know about metric measurements, let's take a second to look at accuracy, precision, scientific notation, and significant figures. In scientific notation, it's a shorthand for writing really large or really small numbers. All numbers are written with a coefficient, which is between the numbers of 1 and 10, times 10 to an exponent. Remember, if the exponent is positive, it is a number greater than 1, meaning that it's a large number, kind of like this number. And if the exponent is negative, then we're representing a number smaller than 1, but less than 0. So it's a decimal number that we're using to represent. So let's take a second and look here at the numbers given. What we want to do is we want to move our decimal left or right until we can form a number that is between 1 and 10. So I'm going to move my decimal to the right until it gets to here. This makes a base of 7.60. So I write down my base, 7.60, and that's times 10, and then we have to find the exponent number. The exponent is determined by the number of spaces the decimal moved. Here, our decimal moved 1, 2, 3, 4, 5, 6 places to the right. Since our number is less than 1, it's 7.60 times 10 to the negative 6. I remember whether or not I have a negative or positive number because once we're in scientific notation, the negative sign indicates that in order to change my number back into a standard number, I'll have to move my decimal towards the negative end of the number line. Let's look at the next example. In this example, we're going to have to move our decimal so we can form a number between 1 and 10. So we're moving our decimal, which is here, towards the left. We're going to move our decimal until we get the number 4.098. Okay. Now again, we have to count how many places we moved our decimal to the left. Our decimal was initially to the right of the last 0. So we moved our decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places to the left. Since our number is greater than 1, we're going to have a positive exponent as times 10 to the 11. Again, I remember this because given my number in scientific notation, in order to convert it back to standard notation, I'm going to have to move my decimal towards the positive side of the number line. Now let's take a second to review significant digits. Above you'll see the basic rules, the Atlantic and Pacific rule for determining the number of significant figures in a digit. So what really are significant figures? Significant figures refer to the number of increments found on a measuring instrument. The more increments, the more significant the numbers in the measurement. So here we have an example using these nails, and we're measuring them with 2 separate rulers. The first ruler has more increments than the second ruler. So when measuring with this first ruler, we can see that the measurement is definitely greater than 4 centimeters, and we can even see the 10th place, which is probably about 4.4 centimeters. And then we'd have to estimate 1 digit beyond where we see. So this would be 4.41. The last digit, the estimated digit, can vary from person to person, but it still must be included in our measurement. If we look at the next example, here we notice our ruler has less increments. So this measurement would be 4 point, and then we would estimate the 4. So notice that the number with ruler A has 3 significant digits, while ruler B has only 2 significant digits. Now there are rules for how to express the number of significant digits in a calculated answer. In this class, we'll use a calculator to find our answers, but it's important that our answer is no better or no more significant than the numbers that went into the mathematical operation. So there are two separate rules for calculations and significant digits. For addition and subtraction, the rule is the answer can have no more decimal places than the number with the least number of decimal places in the problem. So addition and subtraction, again, we're looking at the number of decimal places. But for multiplication and division, the rule is that the answer can have no more significant digits than the number with the least number of significant digits. So multiplication and division, we're actually looking at the number of significant figures. Let's take a look at a few of these math problems. Now I've listed the calculated result from my calculator for all of the math problem examples. But let's look at the first addition problem. In addition, again, we're looking at decimal places. So we see that for this number has 2 decimal places, this number has 1, and this number has 2. So our answer can only have 1 decimal place because this number only has 1 decimal place. That means that our answer must be rounded to just 1 decimal place. So to round this number to 1 decimal place, we'd end up with 10.3. The reason why it would be 10.3 is we want 1 decimal place. We look 1 place beyond. Since it's greater than 5, we'll round up. In the next problem, we have this calculated answer, but we have to round it according to the number with the least number of decimal places. So this number has no decimal places, this number has 2 decimal places, and this one also has 2. So we need to round this number so it has no decimal places. So that means we're going to keep these numbers. We're going to look 1 place beyond to determine rounding. Since this is a 3, it's less than 5, we're going to stay. So we're not going to round up, but we're just going to stay. So our answer becomes 7,638. Now for multiplication and division, instead of looking at decimal places, we're looking at significant figures. So this number has 4 significant figures, this number has 2, and this number also has 2. So our answer can only have 2 significant digits. If our answer has 2 significant digits, we're going to keep these 2 digits, refer to the next digit for rounding, so our rounded answer is actually just 4.8. And finally, in the last example, again it's multiplication and division, so we're looking for the number of significant digits. This number has 4 significant digits, this number has 3 significant digits, and this number only has 2. That means our answer can only have 2 significant digits. So we're going to underline the first 2 digits. We're going to refer to the next digit for rounding. So that would be a 2, and then I'll round up, so this becomes a 3. But 23 is nowhere close to 22,556. So in order to show the magnitude of the number, I'm going to put insignificant zeros as placeholders. I could also rewrite this number in scientific notation, or 2.3 times 10 to the 3rd power. This is the power of scientific notation, is I can write numbers without insignificant zeros. Now let's apply these concepts to some practice questions. Question number 17 from your review sheet asks, which mass measurement contains 4 significant digits? So since there's a decimal present in choice A, we're going to approach from the Pacific side and we're going to cross off zeros until we hit the first significant digit. So A has 2 significant digits. Now in choice B, again we have a decimal present, so we approach from the Pacific side of the number till we hit a significant digit, and then we count the rest. So B has 3 significant digits. In choice C, there's no decimal present, the decimal is absent, so we approach from the Atlantic side. Choice C has 4 significant digits. And choice D, again, has no decimal present. We approach from the Atlantic side of the number till we hit the first non-zero digit and count the rest of the digits. That's 3. So here, our best choice is choice C. In the next question, we're asked to give the correct reading of the thermometer. We can see from the zoomed in portion that this number here is 0. So we can see that each major tick has a place of 1. So in this case, this has a measurement of 4. But remember that whenever reading an instrument, we always have to estimate one place beyond where we see. We can see that the measurement is between 4 and 5, so we have to estimate a digit. So we could say 4.5. Notice now, my answer that I've just generated is not found below. But the important part is my answer needs to be in the correct number of significant digits. So it should be 4. Remember that the final digit of our measurement is always an estimate. So 4.5 is very similar to this value, 4.3. The next question has us doing a metric conversion, and they ask us which quantity in joules. How do I know joules? Because down in the problem, all of my quantities have a J for joules, is equal to 50 kilojoules. In order to do metric conversions, I typically use the mnemonic device King Henry died unexpectedly drinking chocolate milk, and then we could also add with 3 monks, 3 nuns, and 3 priests, though we won't need those units at this time. So what we're going to do is we're going to see how many jumps it takes to move from kilo to our base unit. We know that joules is a base unit because it only has one letter in its metric abbreviation, meaning there's no factor of 10. So here from the mnemonic device, we see that we should move our decimal place 3 places to the left. So that means that we'll take 50 and then we'll move it 1, 2, 3 places, drop it down to the left. Now, so this number needs to be written in scientific notation. To write the number in scientific notation, you're going to move your decimal back so that you have a number between 1 and 10. So I move my decimal to here to create the number 5. And so it'll be 5 times 10. And then I'll see how many places did I move my decimal. I moved my decimal 4 places, and this number is greater than 1, so it's going to be 10 to the 4th power. Now remember, the alternate way to do this metric conversion is we'll write down the unit we began with, which is kilojoule, and we'll write down the unit we want, which is joule. We'll use table C to find the factor of 10. Notice there's no factor of 10 for the base unit because that's 1, and we'll multiply that times our given number. When we place this in our calculator, we get the exact same result as we did from using our mnemonic device. So choice D becomes our best answer.